All right, so now let's prove the last result in our very last video for the chapter. Suppose we have a subfield of C, then every irreducible polynomial over K is separable. Okay? And again, this might make you think like, well, what's the point of defining separability? And the answer is, well, it will show up, but over characteristic P, this is not automatic. So it is something that you need to check when you have a polynomial if you're going to try to apply some of the machinery we're going to develop in the next three chapters. What is it? Well, suppose f is an irreducible polynomial. Over k. Then f has multiple zeros if and only if f and df have a common factor of positive degree. That was the point of the lemma that took us a little bit that I kept messing up. Okay, well, f is irreducible. So the only way, and df has degree smaller than f. All right, but the only way that an irreducible guy can share a common factor with an irreducible polynomial can share a common factor with a polynomial of smaller degree is if that common factor is f, right? And the other one must be 0, right? So the only way this can happen is if the GCD of f and d of f is honestly f, but the only way that that happens is if the other polynomial involved is the 0 polynomial. Okay, so if we write f in polynomial notation, then df is 0 . Okay, so this means then that ai is 0 for all I equals 1 to n, because that polynomial must be 0. And this tells us that ai is actually 0 for all I. This tells us then f is a constant. For all I bigger than or equal to 1, f is a constant. And so it has no zeros. Okay. All right, so in particular, the only way they share a common factor is if that common factor is f itself, but that will, and the other one is 0, that will imply that f is a constant. And that's okay because constants don't have multiple zeros. All right, so what have we learned here? Well, every irreducible polynomial has distinct roots when we're looking at subfields of C. And in this chapter, we also learned about normality. And the key thing with normality is that normality is you get normal and finite if and only if you're a splitting field. So if you can, almost all of our extensions are going to be finite. And so what that's telling us is that if we want to show something is normal, we really just have to show it's a splitting field. Now, that's not true in general. It's normal and finite if and only a splitting field. But again, if we know already it's finite, we just need to show something's a splitting field, and that will give us normal. So those are the two well, that's the big takeaway from this chapter is we want to show things are splitting fields. And that is the end of chapter 9.